This fascinating display behind us, you can see, is the back end of the Tandam Accelerator. John, can you tell us a little bit about that?
Yes, the Tandam Accelerator is one of three national science facilities that ANSTO has. One is obviously the reactor, the other is the National Medical Cyclotron, which is at Royal Prince Alfred Hospital, and this is our Tandam Accelerator. It has a pretty interesting story, actually. It began life as a reject from Rutgers University in New Jersey, and is probably a piece of classic Australian recycling. We bought it at a very small amount of money, brought it to Australia and spent several $1 million on it. Now it's regarded as one of the finest instruments of its type in the world.
Right. And what's this display up here on the wall?
Well, that actually shows that we actually get radiation from outside of the Earth. And what that's saying is that we're getting high energy cosmic radiation from the Earth all of the time, and we actually end up taking that up into our bodies. In fact, every living being does. And one of the things we get from that is carbon-14. And carbon-14 is what we use with this machine for carbon dating. And it's one of the things we do. The Tandam is really a very fine analysis machine. Because we know that radioactive isotope carbon-14 decays at a particular rate, and that we stop taking it up, or every living being stops taking it up as soon as you die. If you can count the atoms in a sample, therefore you can find out with a fair degree of accuracy how old an artifact might be.
Approximately, anyway.
Yes, that's right. So, for example, we've done things like dated samples from Aboriginal rock art galleries around the country. You might remember the elephant bird egg that was swept up on a beach in Western Australia a few years ago. We carbon dated that here. A really interesting one we did a couple of years ago was the cathedral at Monza in Italy owns the Iron Crown of Charlemagne, the first Holy Roman Emperor. And they were coming up to an important anniversary, and there was dispute about whether this crown was the real thing. So the crown was iron, which was plated with gold. It was studded with precious stones, and it had a piece of iron inside it, which was reputedly a nail from the true cross. They asked us to carbon date it, and they sent us a couple of micrograms of the beeswax which held the precious stones in place. So we were able to chemically treat those, then accelerate the particles in the accelerator up to 10% of the speed of light, separated everything out but the carbon-14, and we were able to carbon date it to 732 plus or minus 10 years.
So was that the correct date they were looking for?
They were looking for something in that ballpark and accepted it as genuine.
Dr. Andrew Smith, what are some of the limitations of carbon dating that you've found?
Well, the real limitation on radiocarbon dating is that the production rate of carbon-14 has been varying over the millennia. And there is a simple way of correcting for these variations. Scientists have found that by using the technique of dendrochronology, matching ancient tree stumps one to the other, they've been able to establish an unbroken record that goes back 10, 12,000 years before present. And by taking samples of that wood and making a radiocarbon measurement on the wood and comparing it with the actual calendar age of the wood, so you compare the radiocarbon age and the calendar age, you can establish what's called the Stoiber correction curve.
Is this what this diagram here displays?
This is an example of a piece of ancient timber which was growing some 2,000 years ago. And in principle, one can take an individual tree ring, and using the very sensitive technique of accelerator mass spectrometry, we can make a radiocarbon measurement on an individual ring, establishing a radiocarbon age, which we can then compare with a calendar age to make those corrections.
So what sort of strange dates have you had in the past that obviously show you that there was a problem with this method?
Not so much strange dates, but there are periods in history where the curve folds back on itself. So there are certain periods where even though you can make a precise radiocarbon measurement, it is not possible to pin down the calendar age precisely due to the nature of the curve. But fortunately, those periods are fairly rare, and a researcher has to be reasonably unlucky to find that he's plagued by such problems. Here we have an example of a calibration curve, and this one is applicable for the dating of the Shroud of Turin. It goes from a calendar age of 900 years AD to 1500 years AD, and the radiocarbon age is plotted on the vertical axis. And you can see that there is a period where, even though one might make a precise radiocarbon measurement, one cannot say whether the sample belonged to 1300 AD or more like 1400 AD. If one looked in more detail at this curve, one could actually pick out, for example, the 11-year periodicity of the solar cycle. The solar winds interact with the geomagnetic fields to actually provide a shielding effect, and during periods of intense solar activity, the sun helps to shield the Earth from incoming cosmic radiation, which actually results in a decrease in the production rates of radionuclides such as carbon-14 and also the other radionuclides that we measure here at Antares, beryllium-10, chlorine-36 and so on.
But we do more serious work, if you like. You might remember at the end of the Gulf War there were a lot of standoffs between UN weapons inspectors and the Iraqis over access to suspected nuclear facilities. Well, that agency is the International Atomic Energy Agency, and we do a lot of work here for the IAEA using this machine. In fact, they have recently paid for an upgrade in sensitivity for this machine, and they send us samples from known or suspected nuclear sites around the world. We analyse them here, we report back to the International Atomic Energy Agency, and they can make their decisions on whether countries are meeting their obligations under the Nuclear Non-Proliferation Treaty.
This is the main accelerator tank just behind me.
This is the Antares facility. It's a Van de Graaff accelerator, which is designed around a tandem accelerator, which you can see over there. It's about 20 years old, and we bought it from Rutgers University, refurbished it, and now we're using it to do world-class science. The entire facility is basically here to count atoms. Should someone bring us, say, a sample of bone from archaeology, and they want to know the date that it was the person actually died, we can take the carbon out of that piece of bone, put it into what we call an ion source right down the very end, and then we start accelerating the atoms. We take them off the sample and start moving them through the accelerator. We have 8 million volts in the centre of the accelerator, and it'll let us accelerate the atoms to about 10% the speed of light. Okay, in the centre of the tank, we have a voltage of 8 million positive volts, and the atoms actually come through with a negative charge. They get drawn to the positive voltage at a high speed. When they reach the centre of the tank, we take off a lot of the outer shell electrons. We strip them off. We take off enough that the atom actually becomes positive. We then have 8 million volts positive and a positive atom, and they repel each other. Using that, we manage to get a lot more acceleration using the same voltages. And that's why we call it the tandem accelerator. Okay, we have 3 ion sources here. You can see them encaged in the blue cages. Yep. One here, one there, and one way over there. They're all for 3 slightly different purposes. The original one will hold 1 sample and takes roughly 15 minutes to measure it, and another 15 to 20 minutes to change samples over.
So what sort of samples would you be looking at?
That's a very big range.
Just a few examples?
Okay. A lot of our work is actually dating. So we might have bone samples, we might have rock samples. About 3 to 4 years ago, some children in Perth found a very large egg, and we had to actually take samples of that. And we dated that to be about 2,000 years old. And they found that in the desert. Right. We've recently upgraded and bought a new ion source about 2 years ago, and that'll hold 59 samples. So you put them all in at once, and you can rotate through them, and hopefully we should be able to run for about 24 hours before we have to change over. It's just part of trying to become more efficient and becoming slightly more commercial. This is a brand new ion source, and it creates alpha particles, which we can fire down through the tank into a target to learn more about the target itself. And that might be some sort of metallic sample or a crystalline sample. And we can just look inside and investigate it more further.
Hey Bruce, how do you actually generate the ions that you're going to accelerate?
Okay, we'll have our sample and we'll put it in the rear of the machine and we'll put a negative voltage on it. Now, we'll also have a small bulb of cesium. We heat this bulb up so enough that the cesium will actually rise up like a vapour. And as it comes up, it frees off the electrons because it's all heated up. This means the cesium becomes positive easily and gets attracted to the anode. Now, as they get attracted to the anode, they move towards it because it has a negative voltage on it, and they then strike the atoms of the sample. As they strike, you get a reaction sort of like billiards. The heavy cesium atoms go in and strike the lighter carbon atoms on the surface of the sample and knock them back out. Now, as the carbon comes out through the cesium gas, it picks up some of those loose electrons that were left from the cesium. And then it comes up here to where you can see a series of silver rings. Now, those silver rings, they have a voltage on them of up to 50,000 volts. And it's stepped up gradually. Now, this pre-accelerates our atoms. It gives them enough speed to move out through here all the way up to the tank, which you can see over the rear.